Molly.
Good evening, everyone. Welcome to the Astro Imaging channel, and may the 4th be with you, or may the Forge be with you, whichever one you prefer. Or if you're in Australia, like our guest tonight, it's Revenge of the 5th, perhaps, for you. So, so tonight we have with us Luca Quaglia, who's going to be talking about the measuring the eclipse solar radius with eclipse flash spectra. Which is sort of be an exciting topic given the last year's eclipse, and even more ways to get interesting information from an eclipse than you probably have heard of before. Next week, he couldn't stay with us to introduce his topic because he's in Europe and wants to go to bed, but we have Rumen Bogdanovsky next week back again with us to talk about Indigo, which is like ASCOM, but cross-platform, and an alternative to ASCOM that he came and talked about previously, but now there's been more improvements to it and a new sequencing capability with this capturing component of it as well. So he will be on with us next week. Let me share our calendar real quick here as well over on this screen. Upcoming. We have Brad Bush from Bush Labs. I'm still figuring out exactly what he's going to be talking about. Scott Roberts from Explore Scientific will be with us. He's been hosting the Global Star Party for the last, sometime during the pandemic, the last 4 or 5 years or so. So I don't know what he's speaking on yet, but he'll be lots of fun. And then we have Luca Bartek on June 8th talking about doing a script for doing more automated pre-processing in PixInsight. And then we have a whole bunch of open shows. So we, as always, are asking for volunteers to come and speak on the show. So be thinking in the back of your mind during the show what you might be interested in coming on and talking about. And again, we've covered many, many topics on this show. And just because we've covered it before doesn't mean that we don't need to cover it again. Because like I always say, everybody has a unique thing to contribute to that topic. And a lot of our previous topics really need updating. So if you need an idea, go back through our previous topics, which you can also find on our website in the program database, which is a Google Drive document here. And then you might see one from a couple years ago, like, hey, that needs some updating. It's totally different now in PixInsight or in ASCOM or with this hardware, this new thing, Eclipse is that. So be a perfect opportunity to come on and give a talk. So I will stop sharing here. And in order to have even more people be able to see all the goodness on the show, it's helpful to like and subscribe to the channel. We have almost 20,000 subscribers, which is incredible. It's still been growing at a rapid pace. And again, the more people who subscribe, then the more other people will see that content and possibly subscribe. And the more we can talk about astrophotography and all of its goodness to a wider audience. So that is what I have for now. So I will turn it over now to Luca.
Okay. Sharing screen.
Here comes my cat.
Okay. Good evening, everyone, and thank you for this opportunity to present this talk on measuring the eclipse solar radius by observing the eclipse flash spectrum. So I'm Luca, and I'm part of the Besselian Elements Team. So when we look at our star, one of the simplest questions that we might ask ourselves is, what is its radius? And the sun is not a solid object, so the answer to this question is trickier than we might think. The solar radius is more or less 696,000 kilometers. But in astronomy, we are usually accustomed to express distances as angles. So if we place the Earth's center at 1 astronomical unit from the sun's center, so we have a standard distance, we know what is the solar radius. And if we do a little bit of a trigonometry, we can actually compute that the solar radius is equivalent to 959.63 arcseconds. So this value is the standard or canonical value of the solar radius. But where is this value coming from? So it's coming from this publication from 1891 by the German astronomer Auwers. Auwers looked at a bunch of data, analyzed them, and then he writes, the diameter of the sun at average distance, that is to say, 1 astronomical unit, is 1,919.26 arcseconds. If we divide this value by 2, we get the standard radius, 959.63 arcseconds. So this is the origin of this value, which has been used throughout the 20th century and early 21st century. And if you look into astronomy books, this is probably the value you will find. But we noticed that a few years ago, the International Astronomical Union has defined a nominal solar radius equivalent to 959.23 arcseconds. So 0.40 arcseconds smaller than the standard radius. And we also mentioned a few recent determinations. Astronomers have never stopped measuring the solar radius based on Venus and Mercury transits and total solar eclipses. And we have a variety of values: 959.57 arcseconds, 959.99 arcseconds, 960.12 arcseconds. So it makes you wonder, what is the reliability of this 0.63 arcseconds of the canonical standard value? So in our research, we have actually focused on the eclipse solar radius. And what I mean by this, so when we have a total solar eclipse, the time when the photosphere disappears and totality starts is called second contact. And the time when the photosphere reappears and totality ends is called third contact. So what we're interested in is in determining what is the best value for the solar radius that we have to use in an accurate eclipse computational model to predict contact times, second and third contacts, which are the closest as possible to the observed real contact times. And again, because the sun is not a solid body, we don't have a unique definition for the solar radius, but this is what we are aiming to estimate. Here is a roadmap for the talk. So initially, we will delve into eclipse computations, which is the start of this research. Then we will talk about the eclipse flash spectrum, what it is, how we can capture it, and then how we can use observations of the eclipse flash spectrum to estimate the solar radius. And finally, with the knowledge gathered, we will look at how we can improve eclipse mapping and make eclipse maps more accurate based on that knowledge. So I guess most of you, if not all of you, have planned expeditions to last year's total solar eclipse, and you probably looked at websites like this one, or maybe used a mobile phone app to get local circumstances. So for a specific place, you want to know when is the start of the eclipse, when totality starts, when totality ends, when the eclipse ends. Here's an example for the city of Lleida in Spain for next year's total solar eclipse, which will be visible from the Arctic regions, Greenland, Iceland, and Spain. But how do we compute the local circumstances? We all know eclipses happen when the sun, the moon, and the earth are aligned. So we need to know with accuracy the position of the sun, the moon, the earth. We need to know the orientation of the Earth's globe in space. And then we can take all of that and compute local circumstances. So we have our inputs, ephemerides, Earth's orientation, and other inputs. We put everything in an accurate computational model, and we get local circumstances. Here we notice that the accuracy of your local circumstances will be a direct function of the accuracy of your inputs and also of the accuracy of your computational model. And for the last 2 centuries, we have computed eclipses using the Besselian Elements method. And this method was devised by the German astronomer Bessel in the early 1800s, and then perfected by the American astronomer Chauvenet in the mid-late 1800s. And what was Bessel's great idea? So the computation is rather complex because we have a shadow falling on an ellipsoid, which is tilted. And everything is moving, the shadow is moving, the Earth is moving. So Bessel thought, okay, what about if we take a convenient reference system and we do the computations in that system? And this convenient reference system is based on the fundamental plane. And the fundamental plane is a plane which goes through the Earth's center and which is always orthogonal to the axis, the umbral axis at any time. So this plane is actually moving with time, but the outline of the penumbra and of the umbra on this plane is always a circle, just by construction. And this greatly simplifies computations. But this method has an important assumption that the sun and the moon are considered as perfect spheres. But if we look at the moon, we see craters, we see mountains. So the lunar limb is not a smooth, perfect circle, but it is jagged. It is mountains, it is valleys. Here is an example of lunar limb profile. And lunar limb profiles are heavily dependent on the lunar libration, where those mountains and valleys have been magnified to be able to see them. So those mountains and valleys are the ones responsible for Baily's beads that you might have seen last year, but they need to be accounted for if we want accurate local circumstances, because the ones that you get from the Besselian Elements method, they don't include those lunar limb corrections. Here is a reference from 1983 with an explanation of a method of how to compute those lunar circumstances. And in this diagram, you can see this point marked with X. This will be the time when the solar limb is tangent to the smooth lunar limb. So this will be like the time of second contact that you would get from the Besselian element method. But nearby, in reality, you have, in this case, a deep lunar valley. So the sun is actually still, the photosphere is still visible. So the solar limb has to travel a little bit further to get to the real tangency point. So lunar limb corrections are the time needed for the solar limb to travel. And it can be a fraction of a second, a couple of seconds, sometimes 10, 20 seconds. We needed to include those lunar limb corrections. But again, the calculation of the lunar limb corrections will be dependent on our knowledge, on the accuracy of our knowledge of the lunar limb topography. And for a long time, this knowledge was based on this paper, The Marginal Zone of the Moon, from 1963 by Watts. So they were the Watts limb profiles. And we knew that there were inaccuracies in those profiles, in biases, and those profiles were based on images taken, I think, during the 1940s. But the situation changed dramatically in 2007, 2009, when the Japanese Space Agency and then NASA sent probes towards the moon, the Kaguya mission and the Lunar Reconnaissance Orbiter, LRO. And one of the aims of those missions was actually to collect accurate data on the lunar topography. So after those two missions, or based on data from those two missions, our knowledge of the lunar limb profiles has greatly improved. And then local circumstances computations have greatly improved. And here you have an example of another online website by Xavier Joubier, where you can actually see for the same location in Spain, here the local circumstances computed with the Besselian Elements method. And here you have limb corrections on the time of second and third contact. But can we do something better? So can we go beyond the Besselian elements method? Yes. So my friend John Irwin from the UK in 2011 designed a novel 3D eclipse computational method. And in this method, we don't do Besselian elements and then lunar limb corrections, but it's a complex 3D computations which takes into account from the start of the complexity of the lunar topography in 3D on the 3D geometry of the eclipse computations. And this method is nowadays the most accurate eclipse computational method. And in 2017, Ernie Wright at NASA also developed a similar method. And here is a reference from a few months ago, from September last year, where he describes his efforts in developing this 3D computational method. And here we have an example, again, for the same location in Spain, with local circumstances based on 3D computational methods and all the most accurate inputs that we have nowadays. But now we can have make a comparison between those computations. And here you have the time and date, local circumstances. Here you have Xavier's ones without limb corrections, the one with limb corrections, and finally the ones from a 3D computational method, again for that location in Spain. And if you look at the duration of totality, you can see 30 seconds, 26 seconds, 26.8 seconds, and then 21.7 seconds. So the difference is in the computational method, if the method accounts or not for limb corrections for the topography of the lunar limb, but also on differences in the solar radius, which is used in those computations. And those last 21.7 seconds is the duration that you get from an accurate method using an improved solar radius. And this solar radius is the central aim of this talk. So if you have questions, please, this is time maybe to ask questions, if you have any.
Oh, Luca, I
Yes.
have a question. Does this take the topography of the moon take into account its wobble?
Yes, so this this 3D computation will be a full computation that includes relativistic effects, the wobble of the lunar libration, which actually has a strong impact on the lunar limb profile. So, and also this computation will also account for the fact that the lunar limb profile might be different in different parts of the world, the different observing locations. So yes, it accounts for all those factors.
Thank you.
Yeah. There are no other questions. We'll continue with the efforts of our team called Besselian Elements Team. So we started doing researches like in 2007, and we had the idea, okay, we have those eclipse predictions. At the time, there were actually far less sources than nowadays. And we ask ourselves this simple question, can we experimentally verify those contact times computations? Because we had predictions, there were hardly any experimental verification. So for the 2008 total solar eclipse, we designed a very naive experiment, which I have to say didn't work, but it was using a Lego NXT intelligent brick and then a Bluetooth GPS logger. And the idea here was visually observing the eclipse, and then when totality started, pushing a button to record the time of the start of totality, and then pushing a button again when totality ended, and also recording the location. So this manual timing didn't work, but it made us think, how can we improve this setup? So for the 2009 total solar eclipse, we said, okay, we need to record a time-stamped video of the eclipse, and then we can analyze it. So we had a camera. The video output of the camera was sent to this box, which is a video time inserter, and this video time inserter overlaps the UTC time on every frame of the video, and then this time-stamped video was sent to a second camera just for recording. And what we decided to image wasn't the direct image, the white light image of the sun, but we decided to image the eclipse flash spectrum for a series of reasons that we will explore. I have to say we were unlucky, the weather didn't cooperate, so we couldn't get any measurements that time. But then we had a couple of years to think about this experiment, and we said, okay, let's have a look at the accuracy of every input that we put in the Eclipse computational method. So by 2011, 2012, we had a very accurate Eclipse computational method. For the ephemerides, nowadays, they are incredibly accurate. We can use the data from the Jet Propulsion Laboratories, for example, the E440 ephemeris. For the Earth orientation, we have very accurate data from the the Institute of Earth Rotation and System References in Paris. And after the eclipse, we have very precise measurements. Then for the lunar limb topography, we have very accurate data from, for example, the LRO mission. So all this is very accurate, but we don't know what is the accuracy on the solar radius that we put into the computations. So our aim shifted from experimental verification of contact times to estimation of the eclipse solar radius, because we said, if we see discrepancies between the computations of contact times and measurements of contact times, they must be due to the eclipse solar radius, because everything else is known with high degree of accuracy. So for the 2013 eclipse, our aim shifted. We had a similar setup with the two cameras and the video time inserter, and we had a little our little team, Luca, myself from Australia, and John Irwin from the UK, Alessandro Pessi from Italy, Konstantinos Emanuelidis from Greece, and Lucian Kafka from Romania. So we collected a video at that time, but that video had issues, but at least it was a demonstration that we could collect a time-stamped video of the eclipse flash spectrum. And we also did some analysis on it. But how do we image the eclipse flash spectrum? We need to observe the eclipse through a transmission diffraction grating. Maybe some of you are familiar with transmission diffraction gratings if you have a star analyzer for your telescope. And a transmission diffraction grating is simply like a transparent surface with engraved lines on its surface. When the light goes through this transparent surface, most of the energy goes through, and we have a 0th order image, which will be the usual image of an eclipse. But then next to the 0th order image, we have two 1st order images, and those will be the spectrum of the light coming from the eclipsed sun. And here is an example of what we see by observing a total solar eclipse through a transmission diffraction grating. You have the direct image of the eclipsed sun and its spectrum. So initially, even when there's hardly any photosphere left, the spectrum is still very intense, and it's the common spectrum that we know, a continuum spectrum of light. But then as the eclipse is getting very close to becoming total, you can see that a spectrum is slightly emerging, little by little emerging from the common spectrum that we see every day. So the intense spectrum from the photosphere is vanishing, And finally, we have the flash spectrum from the totally eclipsed sun. And this is what we want to image. We want to take a video of this spectrum, of its dynamic behavior. But what we are seeing, we see in the spectrum, it has features. And every feature in the flash spectrum is related to the shape of the light source that has generated that feature. So we have a continuum spectrum that then is vanishing, and that is due to the vanishing Bell's beads, to the photosphere of the sun. But then we see intense arcs, so the spectrum is not continuous anymore, it's like a discrete spectrum. So it must be due to some elements in the atmosphere of the sun. And we also see a very faint round spectrum, which is also due to the atmosphere of the sun. So when the photosphere disappeared, then we are looking only at light coming from the atmosphere of the sun. That spectrum is always there, but it's always hidden away by the intense spectrum of the photosphere. So if we look at we need to look at the structure of the solar atmosphere. And here it's a very simplified diagram. 0 is the surface of the photosphere, if we can talk about the surface of the photosphere. And you can see the concentration of elements at different altitude in the atmosphere of the sun is actually changing. So very close to the surface, like within 500 kilometers, you have all these elements, especially iron and many other elements. Then when you go a little bit further up, all those elements, they become very rare, and you still have sodium. If you go a little bit higher up, you still have magnesium. If you go high up, you still have helium, again, from the surface up to maybe 8,000 kilometers. If you go a little bit high up, you only have hydrogen left. So if we go back to the flash spectrum, then we can see the light from all those elements in the spectrum. So those intense and long arcs are actually coming from hydrogen and helium. Here you have the H-alpha line of hydrogen, then this aqua and blue line, H-beta, H-gamma emissions from hydrogen. The yellow line is the very famous emission from hydrogen. And then we can see those shorter arcs, but still long. 3, this is the magnesium triplet. We see those faint arcs, which are the sodium doublet. And then we have the faint spectrum of the inner corona. And that forest of arcs is the one from iron and all those other elements very close to the photosphere. So here is actually a video of the flash spectrum taken from the center line. You see how quickly this spectrum is evolving. And here it was a spectrum from 2017 eclipse. The eclipse lasted more or less for 2 minutes when nothing much happens. And then if we go towards the end, the moon is moving this way. So towards the end of totality, the atmosphere of the sun on this northeast side of the sun is actually becoming uncovered. So its emission is getting more and more intense. We see intense lines from helium and hydrogen, but then very quickly totality ends. The photosphere comes back, and this flash spectrum is washed away very, very quickly in a matter of a few seconds. So in 2017, we tried to capture a video of the flash spectrum in a much better way than in 2013. So we use a diffraction grating, Canon lens, and a DSLR camera. And when you take a video of the flash spectrum, it's very important to keep the settings constant throughout the video. You cannot do any other adjustments. So once the video is set, it has to go. And here the settings that we found were like the most appropriate, 1/60th of a second and at 100 ISO. So if you want to reproduce if you want to take a video of the flash spectrum, I would recommend to use those settings. And here is the video that we captured in 2017. And I will let it go at with it in real time. You can see the spectrum. Those lines are actually due to the last Bayes beads, which are disappearing. So the continuum spectrum from those Bayes beads is little by little vanishing. And the last one, the last Bayes bead is lingering for a very long time, very, very long time. And then now we are in totality. And very soon the light will come back at third contact. And here is the Bayes bead heralding third contact. So the photosphere is coming back, totality is ended, and the flash spectrum is little by little disappearing. You might wonder why that spectrum from the center line was so quick and our spectrum evolves so slowly. It is because we captured our spectrum right at the edge of the totality path. So we were in Oregon near the township of Vail, less than 500 meters from the southern edge of the totality path. Why did we go there? Because we also realized if we want to do a good estimation of the eclipse solar radius, you need to go to a place where the sensitivity is the highest. So here is an example of how the duration of totality changes by moving away from the center line. So the duration is maximum near the center line, and then it drops away the further away you go from the center line. When you are near the edge of totality, you can actually see the duration is changing incredibly rapidly by moving very, very slightly with your observing location. And here to drive that point again, here you have an example. This was for last year's eclipse in Texas. If you're at the center line, you can move by 3-4 kilometers. The duration of totality will hardly change. If you are right at the edge of the path of totality, you can move by 500 meters and the duration is changed by 10 seconds. So if you move 1,000 meters, 20 seconds, 40 seconds, and then almost 80 seconds if you are 5 kilometers away from the edge of the path of totality. So if you want to estimate the eclipse solar radius, you need to go in very close to the edge of the path of totality. And here's another example, again for the same location in Texas. Blue line is the time of second contact. Red line is the time of third contact. And here is the dependency of the duration of totality with the solar radius. And you see that if the solar radius changes by even 1/10 of a second, your duration is going to change quite dramatically. So again, if you observe from very close to the edge of the path of totality, you have the high sensitivity of the duration of totality to the value of the eclipse solar radius. So now that we have a video, how are we going to analyze this video? So what we want to do is actually, we want to look at the spectrum from the last Bayes bead before totality. We want to select a wavelength, and then we want to extract the light curve from these Bayes beads. And the same thing, we want to do the same with the Bayes bead, which is appearing after third contact. So if we do that, we can actually extract 2 light curves from those 2 Bayes beads. And this is the experimental data that we want to use to estimate the eclipse solar radius. So now we have the light curves, and now we have to look at the dynamic of the movement of the solar limb with the lunar limb. So here you have the lunar limb. Here you have the contact points for second contact and the third contact. They're very nearby because we are near the edge of the path of totality. And the photosphere is disappearing from this valley, reappearing from this valley in this case. So what we want to do is actually to compute, do a simulation of the intensity of the disappearing photosphere and the reappearing photosphere, accounting for all the complexity of the lunar limb and for the dynamic of the movement of the solar limb with respect to the lunar limb. So this is what we want to do. At a certain, and we have to do this computation every second, every half a second. So here, for example, is a certain specific time, the solar limb, and this is the exposed part of photosphere. So we want to integrate this area. But exactly what are we integrating? If we look at the sun, we notice that the sun is more, the intensity is more intense at the center of the sun. But when we move towards the edge of the sun, we have a darkening. And actually, where we want to do this integration is actually very close to the solar limb. So when we do our computations, our simulations, we need to not just integrate a uniform function, but we need to integrate a function that accounts for the lunar limb, but also a function that accounts for this lunar limb darkening. And here is an example of a parameterization of this lunar, limb darkening function. And you can see it depends on the wavelength you're observing at, and this function will go to 0 at the value of the solar radius that you're using. So implicitly in this function, there is the value of the eclipse solar radius. So if you do your computations, you have your experimental light curves, and with the thick blue and red lines are the light curves that you obtain through simulations. So then we can compare simulations to the experimental light curves. And we can do simulation using different solar radii, 959.85, 959.90 arc seconds, 959.95 arc seconds, 960 arc seconds. And you see the best fit is obtained for this value. And we can consider this value and this value like as bordering values. So from that measurement, from the video of the phase spectrum captured in 2017, we actually inferred a value of the eclipse solar radius of 959.95 arc seconds, plus minus 0.05 arc seconds. And if you compare it with the canonical standard value, you see that it's like 0.3 arc seconds larger. So it's actually closer to this value. So if you do computations with the standard value, possibly you are not getting the best results that you could get. And then we had the determination that we tried again at other eclipses to improve our results. And then we tried last year with the Mexican, American, Canadian eclipse. And first of all, maybe some of you saw this eclipse map that was published on April the 1st. It was on April's Fool. And this map of the path of the eclipse was a map that included, that improved eclipse solar radius, and also it included the effect of the topography of the lunar limb. So this was our observation site in Stephenville, Texas, last year. You can see it's very, very close to the edge of the path of totality. We were just 500 meters or a bit more to the edge. So this map shows our observing location, and those lines are actually the northern limit of the totality path from computed with different sources of eclipse maps. So you have time and date, Xavier Jubier, and other websites. And you can see those green, yellow, and purple line are kind of nearby. And those are the lines that you compute just with the Besselian elements. The red line was from NASA. The dashed line was from Xavier using limb corrections. So those two lines, they also include the limb corrections. And the orange line was the line we computed. So you see there's quite a spread. So can we assess the accuracy of those lines? So this, Alessandro, our setup. So the setup we use a diffraction grating, a Canon lens, an adapter, a QHY 174 monochrome CCD camera, GPS antenna, and a Skywatcher Star Adventurer. So here the lens, the adapter, the QHY, and the GPS antenna. The great thing with this CCD camera is that it can put a time on every frame you record. So we managed to record around 10 frames per second. So kind of we have a video of the flash spectrum, and every frame is time-stamped. If you want to repeat this experiment, I would like to suggest a few things. Using a tracking device, because you can do the setting well before the eclipse. You don't want to do the setting just a few minutes before the eclipse. You can focus on sunspots through a solar filter, so you have your focusing well before the start of totality. Then you have to move the camera, find the solar spectrum, and lock the camera onto it. And then, very importantly, you have to rotate the diffraction grating so that the photospheric continuum disappears roughly in the middle of the flash spectrum. This is very important for the analysis. It simplifies your life when you're analyzing. We are extracting light curves from the spectrum. Here is an example of a frame captured with the QHY 174-M. And you see the usual features, the hydrogen lines, helium line, magnesium triplet. This is a very good image. I mean, not super high resolution, but it's great image. And you have the time. So what you can do is actually, we looked at all the frames and we tried to estimate the time of second and third contact from those frames captured with the CCD camera. So what you want to do is to look for the disappearing photospheric spectrum and try to determine when this spectrum is disappearing. This will mark the start of totality. And the same, you want to see when the spectrum is coming back. This is marking the end of totality. So if you do, and you have the UTC timing. So if you do a little bit of comparisons, you can get those approximate second and experimental values for this timing of second and third contact and a duration of roughly 13 seconds, plus minus 3 seconds. So if you remember this value, then we can go and look at the different sources of eclipse predictions, of contact times predictions, and then we can look how well have they reproduced the experimental data. So the predictions that they only, which only use the Besselian elements, well, they are quite far off. The predictions that include the topography of the lunar limb are closer, but still far away. Finally, this last prediction is the prediction from the 3D computational method by John Irwin, and the duration is very close, ballpark close to the experimental duration that we can gather from those CCD data. So we can actually judge the accuracy of eclipse mapping with this method, and we see that the eclipse map, computed by John Irwin, was actually the closest to the experimental observation. But we are always looking for confirmations. So what we did, we're always looking for observations taken very close to the edge of the path of totality. And we found the observation by one of the members of this channel, Jaime Zapata Suarez from Ecuador. And he observed from Texas. But look at the position. So he was inside the totality path computed by all the other predictions, but he was just outside the prediction we published on April the 1st of that year. So this is a very, very interesting location to be in. So what are we expecting? Those predictions will say this observation site is within totality. So we should at a certain point see the Bayes beads disappearing, being off for a few seconds and reappearing. But if this prediction, the orange one, is correct, we should never see the Bayes beads disappearing completely. But we probably see the Bayes beads, a second contact, fading away, and at the same time, the Bayes beads, a third contact, are appearing already simultaneously. So Javier was very kind. He provided us with the image he captured. And here you have a series of images captured certain time, 9 seconds later, 12 seconds later, 16 seconds later. And look what we see. We see Bayes beads fading away. But then at the same time, we see Bayes beads reappearing. So this to me is a hallmark of an observation site which is slightly outside of totality, never inside the path of totality. So if we go back to this map, this is a confirmation that this orange line is actually reproducing what was really observed in this location. And you can also do a more complex computation. Here is the lunar limb, and here is the solar limb at different times. And you can see there's no time when the solar limb is completely below the lunar limb. So there was never pure totality in this location. So I will conclude my talk by saying that if you want accurate eclipse computations, use this improved value of the solar radius, 959.95 arc seconds, plus minus 0.05 arc seconds. This will improve the accuracy of eclipse maps. And also you will need to include the topography of the moon and the Earth in your eclipse maps if you want the best accuracy. And if you want to read more about our research, we published an article in 2021 about the observations in 2017. And then we published a series of articles in the Journal of Occultation Astronomy, looking at the accuracy of eclipse maps and some other efforts of inferring the eclipse solar radius by looking at an annular eclipse. So this concludes my talk, and I thank you for your attention. And if you have questions, I'm very happy to answer.
Excellent. Well, thank you, Luca. Eric, do we have questions?
I'm sorry, I haven't looked. What do we have here?
I'll take a look as well here.
How do they map the lunar surface to the timestamps of their video with a high degree of certainty?
So are you asking about the topography of the lunar limb?
Yes.
Like those satellite missions? I'm not entirely sure, but I think they had like a laser. Like they would send a laser to the surface of the moon and then back. And with the travel time, they can actually map they can build a map of the whole topography of the whole moon, of all the mountains and the craters with an accurate degree, like with great accuracy. So the LRO mission, the Kaguya mission, they provided like an altitude map for the whole moon. And then we can take those data and then we can just look what are the craters and the mountains on the lunar limb. And then we can then compute a lunar limb out of those data. Is it a question you are asking about the timing? Or
I'm not sure. They might be asking about how you line up those when those features are being revealed in the timestamps of your video to the lunar topography.
oh, okay. So
I think they were also asking, how do you calibrate it so that you know that you are all on exactly the same precise time compared to the edge of the moon?
Yes. Okay. So maybe I like. So let's have a look at this image. So the QHY has this GPS antenna, which is then connected to the camera, and then the camera connected to the computer. So the GPS signal has a timing signal, which is very accurate. And the timing signal gives you the UTC time of when the frame is captured. So the QHY is doing the time stamping of every frame. It gets the timing information from the GPS, and then it knows when the exposure started, when the exposure ended for the frame, and in the metadata for each frame, it puts the UTC time of the observation. So time is already built into the metadata of the frame. So that's so we know the exact timing of every frame. And then with that very accurate 3D Eclipse computational model, it's also based on UTC. So when you do your comparison between what you have recorded and your computations, then you are on the same time base. And that is what is doing the matching of the lunar limb with your observation, because your computation is done for the exact same UTC time you have done your observation at. And you probably can see here in this graph, minus 20 seconds, 15 seconds, 10 seconds. So the model is doing the matching between the solar limb and the lunar limb with this uniform time base. Does it answer the question?
He's also
Luca,
asking about how libration plays into this and how you know the current libration.
Oh, the libration. Okay, sorry. Maybe I had misheard.
We were trying to interpret what he's asking. So
yes. So the as I said, the lunar limb profile is heavily dependent on the lunar libration. So when you do your 3D computations, you have your moon as a sphere with all the mountains and the valleys, not just on the edge, but everywhere on the moon. And then you know the exact libration, the exact wobble of the moon at any point in time. And then what you have to do from your observation location, you have to do a projection looking up at the moon and then seeing what are the mountains and the valleys that you see on the limb of the moon. And if you think this computation is a 3D computation, because some mountains could be a little bit closer to the observer, some could be a little bit further, but still sticking out on the lunar limb profile. So the computation is a 3D computation to produce an accurate lunar limb profile as seen from the observing location. So everything is built in this computation.
In,
So
Luca, in this age of
sorry.
in this age of firewalls, are these publications freely available?
Yes, they are all. Yes, they're all available. So this publication is open, and those publications are. Everything is available online. There's no firewall. Actually, what?
Luca, Matthew and Chandrasekhar, are these the ones that are on the screen now? Are those the ones you were looking for? Just
Well,
answer over the comments.
see what they reply back with.
But were you asking?
I think they are.
Referred to earlier in the program.
I think they're referring to these ones, asking if these ones are open access.
Yeah, I'm
Yes.
asking the people who are asking about these.
Mm.
Yeah, I
Luca,
thought it was pre-noted. Is it? Okay.
Luca, you used a CCD camera, not a CMOS.
The one
So we'll be,
sorry.
Yes, the 174.
yes. So I have an admission. I am not like an expert at astro imaging, like most people on this channel are. But yes, like I use this QHY 174-M, which I believe is a CCD camera. I'm not sure, maybe a CMOS camera.
It's a CMOS, yeah.
And CMOS camera. Okay.
It's the CMOS. And the reason
Yep.
I asked that is that you used a 10 frames per second, but that 174 will go a lot higher. Did you select that frame rate?
No, actually, I selected like go as fast as you can in capturing frames, and I try to use a USB 3 port. So try to do everything to have like a fast data transmission. But the fastest it recorded at like a 10 to 12 frames per second. But I have to comment on the speed of acquisition. So the flash spectrum, when you are very close to the edge of the path of totality, is evolving actually at a much slower rate than if you are on the center line. So 10 frames per second is actually quite a lot of points. And so in this, where is the, sorry, I had to get to the, oh, here we are. So these light curves, they were captured in 2017 with the DSLR camera. So the frame rate was 30 frames per second. And you see how many points are on these light curves. So, and this is 30 frames per second. So even 10 frames per second, you will still have plenty of points to do your fitting. So there's no need to go any like 800, I don't know, maybe it's possible, but much higher with the frame rate. I would say it's more important to have a good resolution of your spectrum that you might see in the image. So this is actually a great resolution for the spectrum because I didn't talk about, but A, B, C, D, actually we could map those four continuum spectra from the photosphere to 4 features on the lunar limb. So you can actually see the features of the lunar limb in the flash spectrum in its evolution. So I would say the resolution of the image is actually more important than going to 30 frames per second or higher.
You know, I have to ask you another question.
Sure.
You went to multiple eclipse, but only saw it for a few seconds. Do you feel like you missed out on the 2 or the 3 minute totalities?
So last year was my 10th total solar eclipse. And for my first 7 eclipses, I went to locations close to the center line. So I had my share of experiences. Some were magnificent. Sometimes the weather wasn't that great, but I saw some magnificent total solar eclipses in clear blue sky. And then I decided, for the sake of this research, I need to go to the edge of the path of totality. And for the last 3 eclipses, I went to the edge. So I would say if you are a first-time observer, don't go to the edge, go to the center line, have the full experience. But if it is like your 6th or 7th, then you can actually experience the eclipse from the edge. And I have to say, the experience I had in 2017 from Oregon was an incredible experience because everything slows down. If you have been to the center line, when totality comes, everything accelerates, everything is a rush. But when I was at the edge, everything slowed down. You can see those Baily's beads, they lasted for like almost for a minute, the last Baily's bead before totality. And I could actually see the full solar corona before the start of totality for like 30 seconds. And superposed to the solar corona, there were the slowly fading away Baily's beads. It's like something I've never seen at any other eclipse, and it was absolutely magnificent. So yeah, very different experience, but there's something like beautiful to see even at the edge. And definitely if you want to do this measurement, the edge is the way to go because it's the highest sensitivity you can get.
Yeah, I think that we're all thinking we're going to leave that kind of measurements to you
Luca,
guys.
Luca, towards the end of your presentation, you were talking about where to position yourself. And one of the things you threw in there very quickly was the topography of the Earth. How much does the topography of the Earth matter and where you position yourself? If you're at a mountain at 10,000 feet, how much will the timing be off from if you were in the flatlands right next to that mountain?
Yeah. So the I don't have like a precise numbers in mind, but I know. So we are like preparing a map for next year's eclipse, including all those elements. And like in Spain next year, parts of Spain are very mountainous. So if you go there, you need to include the altitude because you could be like 1,500 meters and your contact times might be different by a second or more. So it's important to include also the altitude of the observation site. The topography of the lunar limb has a great impact, so it cannot be excluded. So computations just using the Besselian elements, especially if you are towards the edge of the path of totality, might be quite noticeably different from the real ones. So everything has to be thrown in together. And I might say last comment, it all depends on the accuracy that you want. If you want your contact times to within a couple of seconds, using Besselian elements is fine. If you want to go further, then you need to include the topography of the lunar limb and the topography of the observation site. And what we are aiming to get is to get to a prediction which is within 0.1 second of reality of what can be observed. And to get to that accuracy, everything has to be included in, including the altitude of the observation site. Otherwise, you quickly lose accuracy in your predictions. And if you want to do photography, I think you need very accurate predictions if you want to time all your sequence of images and so on. So everything is important.
Thank you.
Now, is your value for the solar radius, is that now the accepted value?
Great question. So believe it or not, for last year's eclipse, quite a few of the predictions out there still use the standard radius because this is the value that has been used for like 100+ years. So people are still using that value. And I'm not entirely sure about NASA, but other websites, they use the standard value. So, but I think after last year's eclipse, a few of the eclipse computers around the world have taken notice and they said, okay, we need to use this value because especially this was the, what is it here? This was the observation that gave it away. I mean, we have all these predictions, which edge is the closest to reality, and it's this one in orange with an uncertainty drawn with, because at the end, if we look at the comparison between the predictions and the observation, it's only this prediction that gets closer to the observed value.
You know, it's hard to argue with real data. Huh?
Yes.
Matthew has pointed out something I've been thinking about. I know the sun has weather. Is that weather enough to change the size of the sun? Secondly, when you say it's that far across, that 959, whatever it was, that of course we're sometimes further away from sun, sometimes closer to the sun. So it doesn't actually subtend that angle, right?
No. So we'll answer the second question first. So we are always talking about the solar radius at unit distance. So this value is the solar radius in arc seconds when the Earth's center is at exactly one astronomical unit to the sun's center. So this is the value, the input value that we need to put into the computations. And then the computations will tackle the fact that we might be closer or we might be further away. But we need like a starting point. We need like a standard kind of standardized value. And the standardized value is to express the solar radius when the Earth is at exactly one astronomical unit. So the computation will account for the fact that the sun is a little bit bigger, a bit smaller, but it comes afterwards in the computation. So this is the value at unit distance, which is actually what Alvers also said, the diameter of the sun at average distance, that is to say, one astronomical unit. And for the first question, for sure, the sun is not a solid body. So I'm not sure if like a solar weather could have an impact, but there are several other factors that could have an impact. The sun is oblate and not a perfect sphere. So the oblateness will impact the solar radius because the equatorial solar radius is not the same as the polar solar radius. But there are some researches in the effect of oblateness is less than 1.01, 1.01 arc seconds. So it's actually very, very small. It's on the second decimal of this number. And now we're arguing on the first decimal. So the oblateness has an impact, but it's too small to be seen. And the other thing is you could have at the contact points where you're doing the measurement, some maybe like the photosphere is a little bit higher, a little bit lower because there's like magnetic disturbances. But I think even the effect of those disturbances is actually too small to be seen. Okay. And I will say, sorry?
You're not measuring this photosphere, you're measuring to the limb, correct?
Yes. And actually, when I say that they're like a different definition of solar radius. So here, what we are interested in is what is the input value that we have to put into accurate computational method, an accurate computational method to get the local circumstances which are the closest to the observations. So we need to put a solar radius at a unit distance into this computation. So we are not measuring anything like physical because you will have to have a definition of where the photosphere ends and so on. So here we're just saying, what is the value of this input parameter into the computations that will produce, will give us local circumstances which are the closest to the observed ones. So we are not making any claim on physical, like this is the end of the photosphere or other considerations. We're just saying this is the best estimate for these input parameters. And I can also say, because the photosphere is not like a solid, we have an uncertainty on this solar radius. Yeah, where we have. It's probably at the very end. This 0.05 arc seconds. And this uncertainty is not just an uncertainty of the measurement. It's actually a recognition that the photosphere is not a perfect surface. So I don't think physically we can go any further. We cannot have 10 decimals to this number just because the physical situation of the photosphere. Does it answer your question?
I know when we image, in hydrogen alpha, we see a surface, which is quite distinct, and then a fairly noticeably, I don't want to say thick, photosphere of emissions. So it's unclear, what is that radius?
Yes. So the greater that you talked about hydrogen alpha observations, because we also looked at hydrogen alpha observations of total solar eclipses. And because you have hydrogen in the solar atmosphere, where is the, yeah. So you have a hydrogen in the solar atmosphere. So when you have your hydrogen alpha filter, just letting a very, very narrow band, like very narrow range of wavelengths through, you are actually seeing light which is coming from the photosphere, but also light which is coming from the lowermost part of the solar atmosphere. So the solar radius that you see in H alpha is actually larger than the solar radius we have estimated.
Yes,
because
that was my point. It looks much larger.
Yes, it looks much larger because why to use the phase spectrum? And this image is very clear because what we want to see is when the photospheric continuum is vanishing and coming back. Because this is like what is telling us, okay, the photosphere is completely hidden by the moon. What we see is only emission from the atmosphere of the sun. And actually, as I said, those very faint arcs and forest of those faint arcs are actually coming from the first, let's say 500, 700 kilometers of the solar atmosphere, just above the photosphere. So the photospheric continuum is gone, and you still have the emission from this area, which we call mesosphere. And then the moon moves past, then it will hide the mesosphere and it will hide the chromosphere. So it's actually quite a sensitive measurement because that's why we want to look at the phase spectrum, because we want to be able to distinguish light coming from the photosphere from the light coming from just above the photosphere.
And the amount that is revealed in an eclipse depends on the distance of the moon from the Earth, too.
Yes, by the topography of the lunar limb, by how the moon is moving. Yes, everything is everything is included, and that's why, like phase spectra, they all look different because the lunar limb is different. So the Bayes beads configuration will be different, and you will see different lines which are disappearing. Actually, if you look at here, this was still the continuum coming from those Bayes beads, but you can see they are like a series of lines, and those lines are actually due to different valleys. So the light is coming through some valleys, and there are some mountains that they've already hidden away the light from the chromosphere. So this measurement is quite sensitive, really, and it allows us to dig deeply into all this dynamic between the movement of the solar limb and with respect to the lunar limb.
And how much do proms influence your measurements, or do they?
Sorry, prominences?
Proms, yes, prominences.
Well, you can actually see prominences in the spectrum here. and also on the other side of the sun. So if there's like a large prominences there, it will have like an impact. But again, the prominence will be like mainly, I think, hydrogen. So we can actually see them in the H alpha line, in the H beta line. But then if we then look at the other elements, if their prominence is mainly hydrogen, we can actually take it away, because when I didn't say, but when we extract the light curves, we stay clear from the lines, emission lines from hydrogen and helium and magnesium and sodium. And usually we try to find a region which is very quiet, with not a lot of emission lines from iron and other elements, because we want to separate away the effect of the chromosphere. We want to separate away the effect of hydrogen, helium. So it might be there, but its effect might be lessened, like might be reduced. So it might impact the measurement, but not as much, hopefully.
Okay, do we have any more questions? I think we're good in the chat, and there's no more in the room. Then Luca, well, thank you for coming on tonight and sharing this fascinating story of some awesome science. And let's see. Yeah, don't forget to like and subscribe. If you did think of a topic while we were on the show tonight, you can reach us on the Contact Us button on the website, theastroimagingchannel.org, and pitch us your idea. We'll see if you can come on. And yeah, I think we will call it a night there. Take us out.
Luca, we continue after the program if you want to stay with us a
Forgot to
little
mention
bit.
that to you.
Oh, okay.
Thank you, Luca. It has been a great talk.
Thank you, Jaime, and thank you for your observations.
No worries, my pleasure.
And I said, like, you couldn't have been in a most perfect location.
Yeah, I know.
From what we want to,
It was like
what we want to observe.
very fortunate that the weather pushed us to that location on that day, on that precise day. And for me, it was like a total solar eclipse. I mean, it was not like day and night. We were certainly in certain kind of gray area between what is considered totality and what is not.
Are you going to end the broadcast? I think we're still live.
Yeah.
Oh,
Sure.
That's all right.
Good night, everybody.
Good night.
Bye-bye.